Thank you. Please, at any point, if you all notice I don't have this started, if a friend texts you or something, just let me know. The sooner I do that, the less I have to repeat later. So, just to catch you up stream, sorry, the button. Files tab, all the things are there. First recitation, I'm going to give a couple more attempts. Make sure you're all practicing the problem sets. Where are the problem sets? Oh, look at that. They're in the Files tab. And a reminder to you, there's problem set 1, problem set 2, problem set 3. These correspond to the tests. Problem set 1, test 1. Problem set 2, test 2. Problem set 3, everything left over that'll show up on the final. The final is cumulative and includes everything. If y'all open problem set 1, you will see it is broken down by week. The DC circuit, I just need to update this. DC circuits got bumped to the next one. So you're like, what's up with that? Week 1, week 2, week 3, week 4, week 5, then we have the test. So they're broken down. There you go. And you'll even notice when you do these problems that they're going to look similar to quiz problems. That's like, again, they all build. This problem that we did last class, there's one like it on the test, except instead of 4 charges, it's 3 of them. There's one with 2 charges, placed 0.5 meters apart. Where should you put Q3? That one's also on the quiz. You'll notice, again, the things I have you practice are the things I test you on. They're not always going to be the exact same problem because I don't want to do memorization. But the goal is that on the test, you should look at it and be like, I've at least seen that problem before. If you've done all the problems, that should be the case. Nothing, and I generally have a pretty good track record of that. When I get feedback from students, I rarely, very rarely do I get any concerns that the test didn't look like the practice. Which I'm, glad to hear. That's a major goal of mine. So, great, there's all that. That's my little blurb. Last class, we started talking about electric fields. And the mantra, there's a few mantras here, a few kind of big important statements. Fields cause forces. Fields cause forces. So even though charges don't touch, one charge makes a field everywhere. And when you put another charge in that field, it experiences a force due to that field. An analogy I used with a student that came to my office hours that may or may not be useful is we can almost think of like the sun. The sun makes a light, and that light goes everywhere. It travels outward everywhere in space. But when you look out in space, you don't see that light. You see blackness. You can't see it. When can you see the light that's emanating from the sun? When you put another object in it. Kind of like the same way with electric fields. You can't see electric fields, but when you put another object in that field, then something happens. Kind of like the sun with the light in space and stuff like that. So, I don't know if that's helpful or not. And it spreads everywhere and it gets weaker as it gets farther away. Just like the sunlight gets weaker as it gets farther from the sun. These fields, they were defined in the direction a positive charge would move. So that was the definition of the direction of the field. So they point away from positive charges and they point towards negative charges because that's the direction a positive charge would move. As you get farther away, they get weaker. I already mentioned that. And then we did some things with that. So let me make a little, I don't know if this will be helpful. Important statements. Electric fields, and I'll post these PowerPoints, so this will be there. Electric fields cause electric forces. All charges make fields. One charge makes a field, the other experiences the field. I'm just kind of jotting down all the one-liners that I mentioned a bunch of times. Fields point. And actually, I'll add this as its own. All charges make fields. Fields point in the direction a positive charge would move if it was placed there. And then there's one last statement that I made that is relevant for the entirety of this class moving forward. Negative charges always do the opposite of positive charges. This is going to continue to be a thing in this class. Whatever a positive charge does, a negative charge does the opposite. Positive charges make fields away from them. Negative charges make fields towards them. Positive charges move in the direction of the field. Negative charges move opposite the direction of the field. This is going to keep happening. There's lots of things we're going to talk about that are going to affect charges. Or like next week, one of the things is positive charges move in the direction of, they go from high voltage to low voltage. Negative charges go from low voltage to high voltage. Whatever a positive charge would do, a negative charge will do the opposite. That is a very useful thing. So, if you all remember this statement, and you remember what positive charges do, then just everything of negative charges does the other thing. You don't need to memorize both. Memorize one of them and just flip it if it's a negative charge. My memory is not too great, so this is a convenient way to half what you need to remember regarding what charges do. So, there you go. I'll leave this there. It's a nice little kind of summary of all the major points. Okay. So, here's a picture. I got a charge. My question to you is, at what point is the electric field the strongest? We have point A, which is up to the left, and a little bit, it's closer. B is farther away, and it's up to the right. Which point is the electric field stronger? Go with your gut. I'll give you all a whole minute for this one. Okay, this one. All right, 20 seconds.
I'm not sure.
All right, in 5, 4, 3, 2, 1, 0. Unfortunately, I left my writing utensil at thankfully, I'm not solving any problems today. I'm just circling things. I left my writing utensil in my office, so you all get to see me finger paint today. It does the job. It's just going to be uglier. All right, so it's point A. Why is it point A? It's closer. Here's the way you can also write this mathematically. And I'm going to have to do some typing here. So remember that E equals F over Q. So if I put a pretend charge there, let's just make the value 1. If I put a pretend charge at point A and a pretend charge at point B, the exact same charge, the one that experiences a stronger force is in a stronger field. This is not a crazy statement to make. The stronger your field, the stronger your force. And vice versa. If I get a really strong force, what's causing that? A really strong field. Not a crazy statement to make, but that's the logic there. So, fantastic. Looks pretty good. The farther away you get, the weaker it gets. And you can actually even see that represented by the size of the arrows. It was actually kind of shown in the picture all along. But this one, you're like, but it's not on an arrow. Remember, this is everywhere. These arrows are everywhere. I can't draw an infinite number of arrows on here. This field is at every single point, every single place around it. The closer you are, the bigger those arrows. All right, now we're going to do a tiny bit of derivation. This is pretty simple. I have the utmost confidence in you. Derive the equation for E caused by a point charge Q2. So Q2 is the one making the field. Remember that the electric field equals F over Q. And remember that the force equation is KQ1 Q2 over R squared. So you're going to do a little bit of derivation here. Plug them in. And so is the answer that the electric field is KQ1 Q2 over R squared. Is the equation that the electric field is KQ2 over R squared? Is the equation that is KQ1 over R squared? Or is it this one that's hidden behind this 4 is KQ1 Q2 squared over R squared? Which is the equation for the electric field due to a single charge? Specifically, Q2 is the one making the field. Whatever answer you get, think about whether it makes sense. You should always do that step in every problem.
Every year.
Remember to check with your neighbor. Don't give different answers. What are you drawing or what do you draw? Great icebreaker. You're all doing the same thing. All right, give you all about 10 more seconds. And 5, 4, 3, 2, 1. Now, before I do any math for this, I'm just going to conceptually reason through this. There's only one answer that makes sense. You're going to see what I mean. I mean, of course, there's only one answer that makes sense, but I'm going to talk to you some logic without doing any math to convince you all the right answer without you having to do any math. This expression, it says, find the equation for the electric field caused by a point charge Q2. That's it. It says, find the electric field caused by a point charge Q2. So, there's only one charge causing this field, Q2. That's the only one causing the field. That's what it says. Find the field caused by Q2, and only Q2. So that immediately helps us realize two things. One, we should probably only have one charge present in this equation. Q1 is not even introduced in the problem. It says find the electric field made by Q2. Q1 doesn't exist as far as we're concerned. Q1 is fake. Okay, then the next logical statement is, if the field is caused by Q2, it should probably show up in the equation. Q2 should probably be in our equation if it's the one causing the field. Bigger Q2, bigger the field. Pretty nice logical statement there. So if you all look at these answers, there's only one answer that has a single charge and it's Q2. And it's this one. This is that last step. I actually jumped to the last step. Your answer should make sense. I saw why do you put Q1, and that's okay. We're going to explain why mathematically it's not Q1. But the easy answer is it's not causing the field. Q2 is causing the field. Now, what's up with this Q1 then? What are we going to do about that? So I'm going to put a little text box here. I'm going to type it all out. It's going to be a great time. Normally I'd write it out, but, we do what we can. So, and I'll make this way bigger. This expression, E equals F over Q, there's a few things I mentioned to you all. So if we want the field caused by 2, we're going to put a little subscript there. The field caused by 2. This force would then be, 1, 2. And what is this 1 charge? This is a fake charge that we put there. This is the one experiencing the force. Charge 2 is the one making the field. Charge 1 experiences the force. We don't even, then charge 1, we can pretend like it exists. It doesn't even need to actually exist. So when we have this expression, we can then plug in the equations, and you can see the magic of algebra. So we do that. We divide it by Q1, and I know this isn't going to look as pretty as it could. This Q1 and the Q1 on top are going to cancel. I know this division is like 2 divisions. You can write it out nicer on your paper, and you'll see it does the same thing. And we get that expression. The Q2 is left over. But yeah, again, the beautiful thing here is you didn't actually need to do the math if you just think through what makes sense As Q2 goes up, the electric field goes up. As the distance goes up, the field's going to get weaker as I get farther away from said charge. Again, don't stress it if you miss this. I don't expect every clicker question I ask you all isn't some trivial, every single person gets it right. That's not the point of these all the time. Some of them, yes, it's like, hey, this is something you should all know. This is one of those, hey, this is helping us understand. The reason I do this is so that when I show you the equation, you know why. It's not me just saying, here's the equation. It's one that you actually thought about and built towards. And honestly, you remember things the best when you get it wrong. That's often the case as well. So there's some benefits to that. Yeah. So here's the equation for it. A equals K Q over R squared, where Q is the charge causing the field. R is the distance from that charge to the point that we care about. So we're going to always say, what's the field at this location? The direction is away from positive towards negative. We talked about this. And the last little point here is kind of interesting. If there's a charge at the point where you want to find the field, ignore it. So for example, in this picture, I have a negative charge and I'm saying, what's the field at point P? If there was some random charge here at point P, just because there's a charge there doesn't mean I'm asking for force. That's a thing that sometimes people get in the habit of. They're like, oh, 2 charges, it's always force. If I ask for field, give me field. If I ask for force, give me force. So in this problem, I said, what's the field at point P? I don't care that there's a positive charge there. In fact, that positive charge is not going to contribute to the field at all. And I'll explain that in just a second. A charge cannot make a field where it's located. A charge cannot make a field where it's located. And this is really easy to prove. What's the distance from me to myself? 0. In my equation, if I plug in R equals 0, what happens? It's undefined. You can't divide by 0. So mathematically, we see that. What if you like the limit as R goes to 0? You like we try to do that clever little technique. Then you go to infinity, but you also get all sorts of problems. If there was a positive charge, just hypothetically, that made a field where it's located, and that field was that way, then it's going to push itself that way. And you get all sorts of problems there. A charge can't move itself. That just doesn't make any sense. Which way is it going to move? Like, if it could move itself, how would we determine what direction it is? And that would mean that every single charge in the entire universe would be affecting itself and causing itself to zip around all over the place all the time, and that's a crazy idea. That's not real. So a charge cannot make a field where it's located, because if it did, it'd cause a force on itself, and that's nonsense. Which way would it go? I don't know. Infinite, it just doesn't happen. But mathematically, we also see that at R equals 0, it's undefined, because it can't. So, charges can only affect other charges. They can't affect themselves. All right. So, there's, more, like I've said it about 15 times, they point away from positive charges, they get weaker as you get farther away. This is another slide saying the same thing. And I even mentioned here, you can't do it at R equals 0. So, nothing is really new here, it's just repeating. The things that are important get repeated about 15 times. Okay, the question is, what do we do if there are multiple charges and we want to find the electric field at a particular point? We've kind of done these in stuff. We haven't done fields, we've done forces. What if there's multiple forces and you want to combine them together? Find each force, combine them together. So in this case, every single charge here makes a field. If I label these really, again, it's going to be finger paint, but it'll do the job. 1, 2, 3, 4. The electric field due to 1 is going to point down and away from charge 1. I'll make it a little bit more accurate. So boom, there's the field due to 1. I want the field due to 2, that's going to point towards 2. It's going to be bigger because it's closer. I want the field due to 3, that's going to point towards 3. It's going to be a little bit smaller because it's farther away. The field due to 4, that's going to be up to the right because it's away from it. Hey, I've got 4 vectors. Do some math. Or do some visual algebra, vector stuff. So if you have multiple charges, how do you find the net field? Find it due to every single charge combined together. Just like you all have done at, physics. If you have multiple things, just find each one, and then They're vectors. You have the pleasure of doing, vector addition. What a wonderful time. Break them into components, all that good stuff. If you all are not good at combining vectors, you will need to become good at combining vectors. Vectors are something that every single one of you needs to be capable of. Even comp sci majors, you are going to be like, what am I going to use vectors? You're going to use matrices, and matrices are just many vectors together. Computer science, you all use multi-dimension. Matrices are just a bunch of vectors. And in fact, you work with even more than 3 dimensions, 4, 5, 6, whatever might crazy be. So everyone needs to be good at this stuff. I don't care what your major is, everyone does. So go ahead and try it out. Here's a situation, I got a positive charge in the bottom left, negative charge in the bottom right. My question is, what is the direction of the electric field at that black dot? Nothing is located here. Nothing is at this black dot, and that's okay. Nothing needs to be there for a field to be there. The field is everywhere. But I am specifying this black dot as the point that I want the field at. So is the field up, left, down, right, or none of the following options? There is only one right answer. And you know what? Just to make you all, to hammer this point home, let's pretend there's a negative charge here. Let's pretend there's a negative charge there. It changes nothing about the problem. That's what I want to emphasize to you. Let's pretend that there's a negative charge at this dot. It changes nothing. The problem was the same before I put this negative and after I put this negative. It's the same problem. All right, 30 more seconds. All right, in 5, 4, 3, 2, 1. All right, I am asking for field, not force. Field, not force. When you all are solving these problems on the test, pro tip, like this one you didn't have to do any math, things like that, but when you're solving a problem, how do you make sure you actually solve for the right variable? First step of the problem, what am I solving for? Actually write the variable like E equals question mark. Put that somewhere on your paper so you don't accidentally solve for force. It's a useful practice if you're afraid of messing up. Which one? If it says electric field, put an E. If it says force, put an F. If you write the right letter, you're not going to make you're way less likely to make a silly mistake. So in this case, I said the field of this dot. Fields point away from positives and they point towards negative. So the field's going to point up to the right due to charge 1. We're going to call that E1. It's going to point down to the right due to charge 2. That's called E2. Now, my arrows here aren't perfect. I didn't do a phenomenal job. But if we do our tip-the-tail method, one's up right, one's down left. Which way is my field? To the right. Field, not force. Which way will the force be on this? The other way. But I didn't ask for the force. So the the net field is going to be this way. E, and this is going to be really ugly. E net, great, it's that way. The force is going to be this way. I did not ask for force. Why is the force going to be the other way? Because negative charge is experiencing force opposite the field. Why is the force going to be that way? Because the positive charge is going to attract it and the negative charge is going to repel it. They all connect together. So, remember, negative charges do the opposite of what you'd like. Good rule of thumb. But I didn't ask for force, but I just really want to hammer this because, look, an F and an E are only different by a single line. Like, it's really easy to mix them up. The field and force both start with the letter F. It's kind of unfortunate. Be careful. You will mix these up at some point. All I'm trying to do is make those mistakes as little as possible, as few as possible, and to not be on the test where it matters. All right, let's do another one. And again, I'm going to do the exact same thing. So here it says, what's the direction of the electric field of the dot? I got a positive charge on the left, I got a negative charge in the middle, and then my dot is on the right. What is located at that dot? Absolutely nothing. But just to make sure that that concept that I just told you, let's pretend there's a negative charge there. It changes nothing. But just to keep hammering home the point that fields and forces are not the same. Yeah, you can make up whatever you want there. Yeah, you can put a positive charge there if you want. In which case it's easier. The field will point in the same direction as the force. And I guess just for fun, you know what? Let's make this a positive one instead. Still doesn't change anything. Just for completeness, we'll make this a positive charge. Doesn't matter. Doesn't change the problem at all. All right, give you all about 20 more seconds. All right, in 5, 4, 3, 2, 1. All right, so same thing. We're going to draw the fields. We're going to call this one charge 1 card, this one charge 2. I'm not going to even label the other one because it doesn't matter. This one does not contribute. Whatever this made-up one that I put there doesn't contribute because it's located at the dot. You cannot make a field where you're located. So charge 1 is going to make a field at that point away from charge 1. It's going to be away from it, some size. I'm going to make it that big, whatever that big size is. Charge 2 is going to make a field that points towards charge 2. Now, something I also want to point out here. Notice that I put these arrows as much as possible. I try to put it basically where that thing was, that point was. I started my arrows approximately where that point is. That's really good notation. Why am I mentioning this? If you had instead drawn this arrow over here, it's not in the right spot. It's not where the field is that we care about. It's a good practice that if you were calculating a field or a force or any vector thing, draw the arrow where it's occurring. Draw the arrow where it's occurring. It's just a good practice for organizing your information. All right, charge 2 is going to make a field that points to the left, but it's bigger. Why? Because it's closer. And these have the same magnitude charge, as evident by they're both capital Q and they're both one, I didn't put a bunch of extra signs in them and things like that. So which way is the net field? To the left. Why is the net field to the left? Because I have a big arrow to the left, a small arrow to the right, big arrow wins. If you want to do vector, if you want to do it the visual way, E2 is to the right. Then we go backwards by E1. My net vector is from the beginning to the end. You can still do that visual vector addition to see that. So the answer here is B. And to reinforce this, remember, the field points in the direction a positive charge would move. The field points in the direction a positive charge would move. If there was a hypothetical charge here, which way would it move? To the left. Why? Because the negative charge is closer, and all the rationale we've already said. So, all matches up. Distance matters. Okay. Important question. If there was an electric field inside a conductor, so a conductor, remember, is anything where the electrons are free to move around. There's a sea of electrons inside of a conductor. You can almost think of it like a metal is almost like a water bottle filled with water. That water is the electrons. They can kind of move around freely. What effect would that electric field have on the electrons inside the conductor? Would it have no effect? Would they get pushed in the direction of the field, or would they get pulled opposite to the direction of the field? So, if you want a picture, here's a conductor. It's got an electric field inside of it. There's electrons inside of it. There just is. Always. Every conductor is full of electrons. What are those electrons going to do? Which way are they going to travel? If at all. All right, probably give more time than I need to. Give you all 10 more seconds. It's either you know it or you don't. It's a really straightforward answer. And 5, 4, 3, 2, 1. All right, so this test, do you remember how fields work? Fields point in the direction a positive charge would experience a force. Negative charges do the opposite. That's all you need to remember. Negative charges, when placed in a field, always go the opposite direction. So here's a negative charge. There's my field. Oh, it was working. I was so excited. All right. So my metal pin would serve as a stylus, but it does not. All right, there's my E field. The force will be in the opposite direction. Why? It's the definition of fields. Electrons go the opposite way. Why am I making this statement? This means exactly what it says. If there's an electric field inside a conductor, electrons are going to get pulled. Fun fact, if you have moving electrons, that is current. We're going to learn that in a few weeks. That is electricity in a more colloquial term. But we're going to learn the fancy term for that is current. When you have moving electrons, that is quote-unquote electricity. In our class, we're going to call that current, the flow of electrons. So this means if you have an electric field inside a conductor, you're going to have flowing electrons. They're all going to move opposite to that field, and that is current. That is flowing electrons. That is electricity. Again, to keep connecting those terms together. So here's the thing. When I charge an object, if I put a bunch of extra charge on an object, it doesn't mean that I get electricity, that I get current flowing around in my thing forever and ever and ever. If I charge a piece of metal, it doesn't mean that there's electricity flowing inside that thing forever. Hopefully you can see that would be like a crazy thing. Infinite electricity. You'll charge something and the current just goes forever and ever and ever and ever and ever and ever. No, that's not what happens. So this is an important statement. If that's not happening, if when you charge a conductor, it reaches some equilibrium state, where the charges stop flowing, what does that mean about the electric field inside of a conductor? It must be zero. If it was not zero, they should be moving. If they're not moving, no field. If they are moving, there is a field. And so that's what this slide is saying. The electric field inside a conductor is 0. After some time. If you charge it after some very, very, very short period of time, it doesn't take much time, the electric field inside the conductor is 0. Why? If there was an electric field, it would be moving around. And this would be a current. And that would mean that there's floating charges just in a static piece of metal that I charged once. And that's a crazy idea. Yeah, this is a very, very important statement that's going to get mentioned many times in this class. The electric field inside a conductor is 0. Specifically inside a conductor where you have charged it and let it be, where you're no longer pushing the charges anymore. You just put them there and you walk away. Obviously, we can make current flow through a wire doing other things, and that might be a different story. Electric fields can have an electric field inside, and the reason is yes, this electric field will cause a force on those electrons. It's going to try to move them, but the atoms will hold on to them, so that the forces will cancel. Insulators are holding on to their electrons, so even though the electric field is trying to pull them away, it's not strong enough to yank them from the surface. You can almost imagine they're like stuck to it, sticky to it. Whereas in the case of a conductor, they're all over. They're free to move around, free to flow, wherever they want to go, wherever their heart desires. So that's the difference between insulators and conductors. And this is going to come into play in some problems in the future. One interesting consequence of this, I'm not going to do the demo, but there's a metal cage over there. It's relevant, I'll mention this. This is called a Faraday cage. Named after Faraday. Yeah, I don't have the shocky thing for it or anything like that. But interesting enough, this wire mesh can effectively act like a solid metal. Even though you're like, it's hollow, there's holes. A lot of these electric, so in the case of, we're going to eventually learn at the end of this class that all light is electromagnetic waves. It's electric fields that wiggle up and down, or, depending on your orientation. Your cell phone signal is a bunch of oscillating electric fields and magnetic fields. It's an electric field that oscillates, and if that wavelength is bigger than these holes, it doesn't see these as holes, it sees them as a solid object. So the consequence is if I enter this cage, my Wi-Fi signal is gone. My cell signal is gone. No electric fields can go inside this. Why? Inside a conductor, even if it's hollow, inside a conductor, the electric field is 0. That's the consequence there. That's the really interesting statement there. So, how do you block cell signals? How do you block Wi-Fi signals? How do you block electric fields? You just put a metal conductor around it, and that's going to block it. And that can actually have all sorts of consequences. If you build, for example, a rocket, and you put your radio antenna inside the rocket, and the rocket is solid metal, no signal is going to get to it because of this rule. Even if it's meshed. Another example, well, this is a little different, but your microwave mesh, so your microwave, it uses light, electromagnetic waves. The reason the holes are there in the front is smaller than the microwaves, so it can't go through it. So, to that point, you don't get cooked. Fun fact for you all, I'm going to mention this many, many times there. The same wavelength used to cook stuff in your microwave is the exact same band, it's in the same regime as Wi-Fi signals. Wi-Fi signals and microwaves use the exact same wavelength. The only reason you're not really concerned with Wi-Fi is it's much weaker. No one has a Wi-Fi router that's outputting 600 watts of energy kind of thing. Your microwave uses a lot of wattage, which is power. Just things for the future that are fun that you didn't realize. Tell your friends, Wi-Fi signals, microwaves, exact same wavelength. If you got a Wi-Fi signal strong enough, it would operate the same, but it spreads out and they're not strong. You need a lot of them. Yeah, their wattage is very low. All right. Again, this is going to be as pretty as I can make it. If Q1 is located at x equals 3, can you arrange 2-point charges, Q1, 6.7 times 10 to 6, and Q2, 4 times 10 to 6 along the x-axis so that the electric field is 0 at the origin? And, there's the answer. It doesn't give away anything. Remember, every single problem, first step, what am I solving for? And what I'm solving for here, again, I'm sadly going to have to type it out. I usually like to write it, but, maybe typing will be more clear anyway. Step 1, what am I solving for? I'm solving for where to put Q2 such that E equals 0 at origin. That is the goal. My answer should be a distance. If I ask where should I put something, that's a distance. And in this case, we're using R for distance because it's nice. It's how far away you are from something. It doesn't care about X, doesn't care about Y, any of that stuff. All right, next thing is I'm going to draw a beautiful picture. First step, what am I solving for? Second step, draw a beautiful picture. We're going to need a coordinate axis because we say things are located at specific spots. And we need to know where the origin is, as evident by the statement. So we're going to put Q1 at x equals 3 meters. There it is in all its glory, Q1. And we don't know where Q2 is. However, we do know, and we can even add this to our picture, that E equals 0 here. We know that E needs to equal 0 at the origin. That's our goal. That's our end goal. Make E equal 0 at the origin. So, what's making an electric field there? If I want E equal to 0, is there even anything making it? If not, I don't have to worry about it. Oh, look, there's charges. They make a field. Let's go ahead and draw the field due to charge 1. And I'm going to go ahead and make charge 1 purple instead of red, so it just shows up a little bit nicer. Oh, so sad. All right, it's fine. Boom, there it is. The field due to charge 1 is going to point to the left. Why? Positive charge. Points away from it. So E1. Boom, there it is. Before I even do any math, we should be able to roughly predict where to put Q2 to cancel out that field. We know this is not, E1 currently is not 0. The electric field at the origin is not 0. How am I going to cancel that out? This should be a very obvious thing. I need a field the other way. How do you cancel it? One to the left. How do I cancel to the left and make one to the right? Where am I going to put charge 2 to make that happen? That's the question. So these are the logical steps that you're thinking about when solving a problem. I'm voicing them out loud, but these are the things that you need to be thinking about. These are the steps. We started with what we're solving for. We drew a picture. We didn't think, how do I make this happen? I started adding details, and you build and build and build and build, one step at a time. So where am I going to put charge 2? Somewhere over here. Why? It's a positive charge. Positive charges make fields that point away from them. If it was a negative charge, I wouldn't put it on this side. If it was a negative charge, I would need to put charge 2 on the other side. Now, last step, and again, we kind of already see this. For these to be 0, how does E1 compare to E2? Y'all tell me. They're equal to each other. They have to be. You all know the equations for the electric field. KQ over R. Put those in there, and we built our equation. What do we have? What are we solving for? Drew a picture, put what we had. I didn't actually put the distances. Probably should have put those, but I didn't want to finger paint it because it'd be ugly. Normally I would do that. And you go from there. You build until you get where you want to be. That's how you solve every problem. All right. Have a good one, y'all. Again, practice. There's no substitute for it.
The gridded one?
Oh, one second.